our second problem, and that is the, everyone together, the Chinese postman. Okay, so the Chinese postman problem. So imagine that you're a Chinese postman, and you come to the office, you collect all the letters, now you need to give them out. Okay? All the people live in houses along streets. So you need to visit all the streets, all the little roads, all of them. But you want to have the shortest route possible. Okay? So going back, we can actually solve these problems. And this guy, Michael Kwong, in 1962, came up with this idea how to use graph theory to solve this. Okay? Imagine that we're solving a very simple graph. Okay? 4 vertices. Okay? I'm not really worried about these vertices here. What I'm interested is in the edges, because the edges are like the streets. So imagine I'm starting at A, that's where my office is, and by the way, I didn't say, you start at A, go through all the streets, and gotta come back to A. Okay? If you listen to my video introduction, what we're doing is a circuit. The circuit is you start and end in the same place. Okay? Now, the solution here is very simple, isn't it? I'm going to go from A to B to C to D back to A. Or A to D to C backward. It doesn't matter. Okay? That's going to be the shortest one. I've covered all the edges and I only covered them once. I didn't have to repeat. Okay? Which is perfect. Okay? If you manage to find a circuit that you covered each edge just once, only once, do you remember what you call that circuit? Eulerian. Eulerian, yeah, I don't know how to spell it. We call it Eulerian in Hebrew, but I don't know if it's Eulerian. I'm not sure, and I'm not sure if I'm spelling it right. But you're right, the Eulerian circuit is a circuit, okay, where you did each edge only once. You didn't need to repeat. And there is the Euler Theorem, which I think I told you in the video, I'm pretty sure, that guarantees you to find a Eulerian circuit if all the degrees are even. If you have a graph where each degree, remember degree is the number of edges coming out of each vertex, each degree is even, then you'll find a Eulerian circuit. So the degree here is 2, 2, 2, 2, all good. Okay? So if you have a Eulerian graph, and then by the way we'll call it the Eulerian graph. So a graph that has a Eulerian circuit, we call it the Eulerian graph. If you have a graph where all the vertices are even, okay, then you know there will be a Eulerian circuit, and that's going to be your solution for the Chinese postman. Okay? And then all you got to do is just add up all the edges, because you didn't have to repeat all of it. Anyway, okay? Unfortunately, you're not going to find that in the test. In the test, it'll make your life a bit harder. So, more like this. Okay? Here we've got a graph, and you can see the degrees are 2, 2, 2, 2, 2, 2. But there's a degree of 3 here, and there's a degree of 3 here. Good, well done. Okay, so if you have a graph where you have all the degrees are even, apart from 2 that are odd, then you're not going to find Eulerian circuits, you'll find Eulerian path, which means you start at 1, cover all the edges, and then get to the other. You can't come back. Okay? Now, so that's what do we call that? Semi-Eulerian. Okay? Only thing is, I don't want to do a path. I want to do a circuit. I'm starting at the office, and I need to go back to the office. So that means if I have that situation, I will have to repeat something. I'll have to repeat an edge. So what I'm going to try and do, the algorithm that we're going to work on, is to find that shortest circuit. Okay? Right, before I show you the problem, the algorithm, there's obviously more situation. There could be a situation where there's more than 2 degrees. No, actually, let's just leave that. We leave that for later. Okay, but for now, we just have two vertices with odd degrees. What you're going to do then is find out what is the shortest path from from the 2 naughty vertices, the ones that have odd degree. Yes. Okay, I'm just going to pause here. Right. So again, just to make sure we're clear, I'm identifying the 2 points where we have odd degree. In this case, is I and F. And my aim now is to find the shortest path from I to F. I don't have a direct route in this case. Sometimes I will, but in this case I don't. So I need to explore. I have certain possibilities. I can go, for example, from I to C to F, right? From I to C to F. How much will that take me? What will be the number? Okay. I can go from I to H to G to F. 5, 9, 18. That's a bit bigger. That's not useful. Okay. I can also go from I to A to B to C to F. And that's not going to help me, right? Because if I went from I to C, it would be 5. But if I went to A to B to C, that would be more than 5. So that's not going to help me as well. But there's one more option. Can anyone see? There's one option that I haven't done yet, and that is quicker. I can go from I to C. Then how do I get to F? To D to E. Okay? So that will be 5 plus 1, 6, 8, 9. And that's less than 10. Okay? So, what do I do now? Once I realize what is the winning one, the shortest one, I need to double it. I'll show you what it means. Okay? So I'll give it another analogy so you can do as well. So what I'm going to do, I'm just going to repeat that path. So if there was, from I to C to D to E to F, I'm just going to add another line, like a parallel line. And then from C to D, D to E, E to F. Why am I doing it? The algorithm tells me that I will have to repeat a certain path. Because I don't want to do a path, I want to do a circuit.
You want to repeat the shortest.
Correct.
Section.
The algorithm, the maths, we haven't proved it, okay? There is some amazing proof. I don't know how you prove these things, okay? We'll leave it to the university guys. But it can be proved, I guess, that the shortest path will be the one that connects the 2 odd degree vertices. So once I identified which out of these is the shortest one, I need to double it up. Why am I doubling it up? Because I now have to go on it twice. Now, it's one book I noticed that this process, what we've just done now, doubling up a certain shortest path, is called Eulerizing the Graph. Why do you think it's called Eulerizing?
Because it makes it an Euler circuit.
Exactly. Now, check out the naughty, remember the naughty vertices? This used to be 3, now it's 1, 2, 3, 4. It's odd, they're even. 1, 2, this one remained, it was even, it still remained even. 1, 2, 3, 4, 5. But this one was 3 and now it's 1, 2, 3, 4. So now all my degrees are even. Obviously it's made up because I added these edges, it's the same one. Now I should be able to find an Eulerian circuit. Okay? And how to find that circuit is not a problem. I think last year you might have learned it's called Euler's algorithm. It's honestly, there's nothing even to talk about here. All you got to do is, let's say, tell me where do we start? Where's our office? A. So let's say A is the office. So what I'm going to do now, I'm just going to, I do it like this. I start walking and I sign so I know I've done it already. Instead of crossing. So let's say go from A to B. Then I'll go here. That's not good. Okay, I need to go back to him, so it's fine. I'm not going to go back to him because I finished it, so I'm going to go now. Go back to him. And back to him.
So you don't have to look at the shortest.
Well, what I need to do, the answers, there will be 2 answers. First of all, I need to write down what the path is. So I was very careless here. I just showed you the path. I should have at the same time write down what path I did. Okay? So, I will do that now with blue. Okay? Starting from A. I'm not going to do the whole thing. But the way I will do it is, okay, I'm going to go to B. Okay? And now I'll write A to B. B to C, right to C, C to I, to H, carry on, carry on. And by the time I crossed all the lines, I know I've covered all the edges. Okay? So that's one part of the problem, of the solution. Okay? To write down the path I actually take. The other, what would they ask you in a question also is, what they're going to ask you? The distance. What is the shortest distance? So then I can either, just as I write that, I'm going to add, okay, A to B, 3 plus to C plus 2 plus, just add it up. But actually, you don't even need to do that. If they just ask you the shortest distance, you don't even need to go through all this. Because you know, you've got all the edges. All you've got to do is just add them up. Because you know you have to cover all of them, isn't it? So you're going to say 2 plus 5 plus 4 plus 9 plus 1 plus 5 plus 2 plus 1 plus 5 plus 5. Because you know you're going to repeat that one. There's some that you're going to repeat. You're going to repeat this one twice. You're going to repeat that one twice. You're going to repeat that one twice. You're going to have to do both of them. We alright with us, guys? Okay. One more difficult example. You don't need to copy everything. Okay, right. So, our second problem, which is a bit more difficult. So again, we've got a graph. We are going to start from, I don't know what, starting and ending at A. Okay, so we start and end in A. We are the tiny postman. Okay? And we want to find out the shortest circuit. Okay? So the first thing I need to do is do what? What's the first thing?
Find the odd number.
Find out if there are any odd numbers. Maybe, you know, if everything is good, Olivia, maybe everything is even, then it's not our problem. Okay? But unfortunately, you're right. There are some odd numbers. So who are the odd ones?
D.
D has 3. F has 3. H and B. So we don't have 2, we actually have 4. Now there is a really interesting, we call it a lemma. It's like a theorem. I don't think I mentioned it in the video, but I saw it in another book. I don't think you need to remember it, but it's an interesting one. So you could have graphs with odd vertices, absolutely, you could. But there is absolute guarantees that the number of odd vertices or vertices with odd degrees will be an even number. Yeah. And you can try that as a little homework if you want extra. Try and draw a graph where there's just one vertex with odd degree or 3 vertices with odd degree. You can't. Because think about it.
Go somewhere.
Exactly. So if I've got a vertex and I want to give it an edge, so it will be 1, but then I have to put the vertex there. Okay? It's called, interestingly enough, the handshaking lemma. Because you always have to shake somebody else. So if you're odd, he's going to be odd as well. Anyway. So we have 4 odd degrees. 4 vertices with odd degrees. So we can't, you know, what did we say? We need to find out the shortest path between the 2 odd ones. But there's no 2, there's 4. What we got to do is create 2 pairs. Okay? So we need to find out, we basically need to pair them up. That's what we need to pair them up. We need to find 2 pairs, find the shortest path between 2 pairs. But it could be between B and F and D and H, or B and D and F and H, or F and D and B and H. We're going to have to check it all. Okay? So let's start with pairing up D and B, DB and FH. Okay? So D to B. I can either go from A or from E. Which one will be? That's 8, right? Okay? So that will be 8. Write it like this. 8 plus F to H. F to H, what will be the shortest one? I think 10, right? Either 10 or 11. You with me, guys? Okay? Tell me if I'm going too fast. Okay, that's 18. So I'm adding them up. Okay? Next one, let's pair D and H. So D and H, that means B will be together with F. Okay. D and H, 12 or 12, well, it's 12 either way. B and F, either 7 or 10. So I'll go with 7, 19. So not so good. Okay? next one, I've paired already D with B, I've paired it with H, so the last pair I have is D and F. And that means B will be paired with H. D and F is either going to be 10 or probably much bigger things, so I'm not going to even try. So it's going to be 10. B and H is 9. So 19. Okay, so I had to try all the different pairs and all the different parts, and obviously that one is the one that won. So D is going to be connected to B, and F connected to H. Okay, that's the winning one. Now, what do I do at this point? Once I know the shortest path is 2 and 6, and F to H is, where's F and H? F and H, we said, is this one. So what do I do now? Once I identify, you double them up, okay? So I'm going to double up. I'll use the black one. So it's this one and this one, okay? And then F and H we're going through E. Okay? And what I've done now, I've Eulerized it. Okay? I didn't write it before, but maybe it's a good idea because I've got 2 is the edge here. This edge is also 2. This edge is also 6. This edge is 4. This edge is 6. Okay? And what I'm going to do now, I'm going to do it the other way around. First of all, let's try and find out what is the total path. I'm going to do the total path. I'm just going to add it all. Okay? So maybe one of you can have a calculator and we're just going to add it up. Okay? Right, so I'm going to add 2 plus 2. Okay, so we do it 4 plus 12. I'm repeating these ones, yeah? 4 plus 12 plus 7 plus 3 plus 8 plus 3 plus 12 plus 12, those two, plus 11. 84, we hope so. Okay, 84. They got 78, so we made a mistake. But never mind. Okay? Anyway, you got the idea. You got 78. Right. Okay. Anyway, that's to find the path, the distance. Now, if you want to find the path, okay, so you know it's actually better if there's 2 people. One does the wobble, 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 and the other one writes. Okay. I like doing the wobble, wobble. So where are we starting at A? You want to start from A, so you can go wobble, 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 wobble. Okay, and I'll write down A to B, wobble, 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 wobble to C. And now I'm going to give up on this one. I just want to do wobble, wobble. Okay. Okay. Doesn't matter where you go. You'll manage anyway. Wobble. You notice, by the way, I didn't mention anything about this. We keep coming to the same vertex. That's fine. It's no problem. Our Chinese postman can come to the same junction. That's no problem. Okay? Reason I'm saying that, next year we're going to deal with Hamiltonian problems where you don't want to repeat the junction, but you can repeat the edges. It's a different story. Wobble, 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 wobble. Go back to it. Ta-da!